So our next section to discuss are chemical equations. And a chemical equation is a written representation of a chemical reaction. So a chemical reaction produces a new material by rearrangement of atoms. That is our supporting our chemical changes, and we want to express how those changes occur through the equation. There are parts and positions of equations that we need to be aware of. The first part are reactants. They are the materials that are about to interact located on the left side of the equation. So they are our beginning parts or our starting point. The other part of our reaction is called a product. It's the newly formed materials on the right side of the equation. So a product is what is being formed, and the reactants are what are going into the equation. The other piece that we need are called coefficients. They are numbers in front of the chemical formulas to show the ratio in which reactants combine and products form. So they're telling us how many of each item needs to go into the reaction so that we have a balanced equation to show that the matter is being transformed but not creating new matter, and we're not losing matter. One thing to keep in mind, if the coefficient is 1, we do not write it. So the coefficient 1 is omitted from our reaction. By saying it, we have it. By writing it, we have it. We do not need to put a 1. So think about a math class. Do you say 1x squared? You just say x squared. If you have more than 1, then you start using a coefficient. There are other notations and symbols that we use, and the atomic and molecular formulas are used to represent the products and reactants. So we don't just always say the words, we actually use their symbols and their formulas. We can indicate the phases of matter, so we can show those with abbreviations, and yes, we do use parentheses. So S is for solid, L is for liquid, and G is for gas. There's another one that we use called aqueous, and that is when we have something that is normally a solid, but it's dissolved in water so that we can use it to react. The third item that we see is the plus. That means we're adding, so it's just like math class, it's our plus for addition, or it means and. So we say we have water and carbon dioxide, or water plus carbon dioxide. An arrow pointing to the right is our yields or produces. That's the equal sign for chemistry. So it's just like saying equals, but we're saying it forms this, produces, or it yields. An arrow pointing up means that gas is given off during a reaction. So you may see that in some of our equations. When we perform equations, we have to worry about the law of conservation of mass. Matter is neither created nor destroyed in a chemical reaction. Atoms just switch partners to form new molecules, so we're rearranging all the atoms to make new items. We used balanced equations, where each atom must appear on both sides of the arrow the same number of times. So a balanced equation is indicating that law of conservation of mass. Coefficients are used in the equations to tell us the number of times the elements in a compound must be counted, or how many molecules or compounds are used. So for all balanced reactions, or all reactions, they need to be balanced. We need to have equal parts on both sides for each atom, each element of an atom, and we do that by adding coefficients to the equation. We'll be working on balancing equations in the next segment. So we have 5 basic types of chemical reactions. Yes, there are more, but we are not going to go into those. So we're going to stick to our 5 basic types, and they are the most common reactions that we see. The first one is called a combination or synthesis reaction. This is where we have simple molecules joining together to form more complex molecules. So a way to look at this is we have magnesium and we have oxygen. Usually when we do this, we burn it, and what we get when what's left over is magnesium oxide. So we have this nice shiny gray metal reacting with oxygen during burning to form a white powdery ash called magnesium oxide. Ways to represent this in a generic way or as a pattern, we would say A plus B yields AB, Or we could have more than just elements. We can say A plus BC yields ABC. So the first example is showing two elements forming a compound, and the second example is showing an element plus a compound making a more complex compound. The opposite of that is decomposition. Decomposition is when we have a larger molecule breaking down to form simpler molecules. So an example is we have water breaking down to hydrogen and oxygen. So that pattern would be the opposite, where we have AB, one compound, breaking down to two individual elements, or we have compound ABC breaking down to a compound plus an element. So one of the things to keep in mind, so let's go back here. In combination reactions, you always have one product. So when you look at it, classify what you're seeing. We are seeing for Mg plus O2 yields MgO. We are seeing one element reacting with another element to make one product. The key there is the one product for combination. When we look at decomposition, we see we have one reactant and it makes two or more items. So it's one reactant, one compound breaking down to form two or more elements. So our water is a single compound and we are making hydrogen and oxygen. We are making two things. So the key there is only one reactant. Single replacement is when a compound mixes with an element and that element replaces one of the substances in the other compound. So when we look at this, we have zinc and we have HCl. So what happens is the zinc is jumping in and hydrogen is jumping out. So now zinc is with chlorine and hydrogen is by itself. So zinc is coming in to the HCl, hydrogen is jumping out. So zinc is replacing hydrogen in this reaction to form zinc chloride and hydrogen. So when I think about this one, I focus on both sides. Once again, like we did the other two, let's look at the reactants. In pattern A, we have an element and a compound, and we have a compound and an element. In the next one, example, notice we still have an element and a compound and an element. So on this reaction, both sides have to have an element and a compound for going in and coming out of the reaction to be a single replacement reaction. Our next reaction is called a double replacement reaction, and I have learned this as being two compounds in aqueous solution. You can't just smash two salts together to make something new. So we do have them in water. And if you recall, in a lot of our labs, we've been using dropper bottles. So that frees up the ions. Whenever you put these salts in water, it frees them up so they can react and bond to other things. So during double replacement, we have two compounds in aqueous solution, and they also exchange elements. But this time it's a buddy system. So I think of this as in math class, we have the FOIL method. So I say in chemistry, we have the OI method. So we have magnesium here. He's going to partner up with HCl. So that's our outers. And then we have the inner here, hydrogen, pairing up with carbonate. So we have our outers, magnesium and chlorine, and then we have our inners, hydrogen and carbonate. So here are the outer substances, here are our inner substances. So that is double replacement. And if we look at the generic equation, notice it's AD over here, and then we have CB over on the other side. The C must always come first because it came first here, so it's a cation. Metals have to be written to the left. So if you decide to rearrange it and you decide to go AD plus BC, That will be wrong. You are changing the formula. Metals must go first. So whatever is written on the left in the original formula should be written on the left when you write the products. Metals have to stay first. So please watch that. Our last reaction, I think, is our favorite reaction because we always get to do fire when we have this one. So a combustion reaction is when a substance combines with oxygen. These reactions always produce energy in the form of heat and light, and we have one or more products that contains the elements in the reactants. What we're showing here is the most common form where we have a carbon hydrogen atom. Okay, so we have carbon and we have hydrogen. So this often happens with organic substances. And we have oxygen. And whenever we have a carbon hydrogen substance here and we react with oxygen, our only options for products are carbon dioxide and water for a full combustion reaction. We're going to stick with this concept for combustion. We're going to stick strictly to the carbon hydrogen concept, but we could actually have CHO something or other. So this carbon would have a number, hydrogen would have a number, and then we could possibly have an oxygen there. And the reason why I bring this up is you can burn alcohols, and alcohols are carbon, hydrogen chain with oxygen in it also. And if we add oxygen to it and then we give our wonderful flame to it or an extra energy source, because we do have flash points, we can still produce carbon dioxide and water. So we can burn just carbon hydrogen chains or carbon hydrogen chains that also have some oxygen in them and get carbon dioxide and water as a product. Notice for this reaction, there is no simple pattern. There are no A's and B's here. We can only show this reaction by using carbon and hydrogen-based substance and oxygen with the products of carbon dioxide and water. So this is the only one where you can't play that A-B game for examples. So that concludes our types of reactions and some basics, and our next focus point is how to balance.